Hello there, and welcome to the Sleepy Science Channel. Tonight, we turn to one of the rarest discoveries of our age. Astronomers have found a new object moving through our skies. It's called 3I Atlas, and it does not belong to our solar system. It comes from somewhere else, another star, another world far beyond our own. In all of history, only 2 such visitors have ever been confirmed. Each stayed only briefly before vanishing back into the dark. Now, a third has arrived, and this time we have a chance to watch more closely. For a short while, we can study a piece of another planetary system as it drifts past our sun. We'll be able to uncover what it's made of, how long it's been traveling, and maybe reveal secrets about the worlds that orbit distant stars. If you enjoy these calm explorations, I invite you to like and subscribe, or simply share a thought in the comments. It helps others find their way here too, one sleepy soul at a time. But for now, allow the day to fade away, let your body soften, and join me as we explore the newest visitor from the stars. This story has humble origins, starting with just a faint wisp of light, almost too faint to notice. In early July 2025, automated sky surveys recorded a tiny speck shifting against the stars. On its own, it was nothing remarkable. But when astronomers compared the frames, the movement told a different story. This was not a star, nor a distant galaxy. It was something closer, something moving. At first, it might have been dismissed as another small comet or asteroid, the kind spotted every week. But the numbers didn't quite fit. Its motion was fast, and the arc of its path looked unusual. A few careful calculations hinted at something more. The speck was not circling the sun at all. It was simply passing through. That subtle trace of movement, almost lost in the noise of the sky, was the first sign of an interstellar visitor. The telescope that caught this faint signal was part of ATLAS, the Asteroid Terrestrial Impact Last Alert System. ATLAS is built to scan the heavens night after night, not in search of beauty, but for safety. Its task is to find anything moving quickly enough to one day approach Earth. The system works by capturing wide-field images and looking for tiny dots that shift between exposures. Most of those dots turn out to be harmless asteroids, looping quietly around the sun. Occasionally, one may come close enough to draw attention. But once in a great while, something stranger appears. On that July evening, it was Atlas that first spotted a body whose motion did not resemble the familiar. A discovery system designed to watch for danger had, instead, stumbled upon one of the rarest opportunities in modern astronomy. The night of July 1st, 2025, will be remembered not for drama, but for routine. The Atlas telescopes, perched in Hawaii, were following their nightly schedule, sweeping the star fields with mechanical patience. The sky near the heart of the Milky Way is crowded, a difficult place to detect faint, moving objects. Yet there, among the countless stars, software flagged a dim speck that shifted between frames. The motion was clear enough to deserve a closer look. To most observers, it still looked like a background star. But to those who had seen many such detections, something about it stood out. Within hours, the data had been passed to astronomers elsewhere, asking them to confirm what Atlas had found. A dot no larger than a pixel had entered the record, a dot whose true nature would only become clear with careful calculation. At first, the dot was classified like any other comet. Its provisional name was C2025P1. But names in astronomy carry weight. They change as objects reveal their nature. As new data arrived, calculations showed that this object was not looping back to the sun. Instead, its trajectory formed an open hyperbole, a one-way path through the solar system. This realization brought a change. The object was reclassified as an interstellar body. Its new name became 3I 2025 P1 Atlas. The 3I marked it as the third interstellar object ever discovered. Atlas honored the system that first saw it. A string of letters and numbers now stood for something extraordinary, a traveler from beyond our star, passing briefly through our neighborhood. To call something interstellar is to say it comes from between the stars. Most comets are children of the sun, frozen fragments orbiting in vast loops that keep them bound to our star. But interstellar objects are different. Their speed and direction reveal that they are not tied to the sun's gravity. They are outsiders, born elsewhere, set adrift when their original systems flung them into the galaxy. When one happens to cross our skies, it is not returning. It is passing through once only, never again. 3I Atlas belongs to this rare category. It is not a fragment of our solar system's story, but of another. To watch it is to glimpse a piece of distant history. To call it interstellar is to acknowledge its strangeness, its independence, and its journey across the vast spaces that separate stars. In all of recorded history, only 2 other interstellar objects have ever been confirmed. The first appeared in 2017. It was given the Hawaiian name Oumuamua, meaning a messenger from afar, arriving first. It had no tail, only a curious, elongated shape, and it sparked endless debate about what it really was. The second, in 2019, was comet Borisov, which looked more like what we expect, a bright coma, a sweeping tail. Now, in 2025, comes the third, 3I Atlas. 3 examples may sound small, but to astronomers, it feels like the beginning of a pattern. Each one has been distinct, each offering a new perspective. With every discovery, the mystery deepens. What kinds of fragments are traveling the galaxy? How many pass unseen? For the first time, we have enough examples to begin asking those questions seriously. News of the discovery spread quickly through the astronomical community. It did not cause headlines overnight, but within hours, observatories had shifted their schedules. Professional astronomers and amateurs alike pointed their instruments toward the faint point of light. The excitement was not loud, but steady. There was a sense of focus, of knowing how rare this chance was. The first interstellar visitor had been too strange, too fleeting to fully understand. The second had been brighter, but still left questions unanswered. Now, here was a third, discovered with enough warning that careful study could be planned. The feeling was one of quiet urgency. No rush, no panic, just the recognition that a window had opened. And for a short while, the universe was offering us a gift. The importance of this discovery rests not only in its rarity, but in what it represents. Our solar system formed billions of years ago, yet it is not isolated. The galaxy is full of exchanges, fragments tossed outward by the birth of stars, drifting until chance brings them close to others. Each interstellar object is such a fragment, a sample from a nursery we cannot visit. When one enters our skies, it offers a chance to learn what other systems are made of, how they formed, and how they differ from our own. 3I Atlas is more than a faint comet. It is a messenger carrying the fingerprints of another star's history. To scientists, its arrival is like receiving a package from across the galaxy, one that can only be opened while it passes by. So we begin this story not with a spectacle, but with a faint signal on a computer screen. A single dot, almost overlooked, has become the center of global attention. Over the chapters to come, we'll follow how that dot revealed itself, a tail spreading in sunlight, a chemistry that startled observers, and a path that confirmed its origin far beyond the sun. This is a story that unfolds slowly, and so we will take it at a calm pace. Each step adds a little more clarity, a little more wonder. For now, what matters is this: a traveler from another system has entered our skies, and for a brief moment in history, we have the chance to watch it. Spotting something like 3I Atlas is never simple. Interstellar objects are small, dark, and move quickly against a crowded background. Most of the time, they are lost in the noise of the sky. The challenge is that they look exactly like faint stars until a telescope catches their motion. Even then, the signal is delicate, no brighter than the margin of error in many surveys. Astronomers must be cautious. A single false reading can mimic motion. But when multiple detections line up, a new story emerges. To follow a faint traveler, you need persistence, wide-field surveys, and the cooperation of observatories around the world. Each frame adds a data point. Each night sharpens the picture. The work is quiet and meticulous, but the payoff is extraordinary. For a rare few, those drifting specks turn out to be visitors from beyond the solar system. The first challenge was the setting. 3I Atlas was discovered against one of the busiest star fields in the sky, close to the glowing center of the Milky Way. In that region, thousands of stars crowd every image, with galaxies and clusters layered on top. Detecting motion here is like spotting a grain of sand shifting on a crowded beach. The faintness of the object only made it harder, yet the signature was there, a steady drift between frames that no background star could mimic. The crowded field that might have hidden it instead served as a stage for its reveal. The tiny motion stood out precisely because everything else was so fixed. What looked like confusion at first turned out to be the proof astronomers needed: a faint speck, moving with a purpose in a sky full of still lights. Soon, larger instruments were brought into the search. One of the first was Gemini South, a powerful 80-meter telescope perched in the Chilean Andes. Gemini's wide mirrors could collect far more light than the Atlas survey cameras, resolving the faint speck into a sharper point. Its observations confirmed that the object was real and measurable, not an artifact or mistake. With each passing night, Gemini's data refined the path. It became clear that this was no ordinary comet drawn in by the sun's pull. The orbit curved outward, not inward, and the velocity was too great to be held by gravity. The evidence was mounting. This was an interstellar traveler. Gemini South's role was to take the first clear snapshots that elevated suspicion into confidence, turning a faint signal into a recognized discovery. As the days passed, a change appeared. The speck was no longer just a point of light. A haze began to form around it, faint but unmistakable. This was the coma, the cloud of gas and dust released as sunlight warmed the icy surface. Soon after, a slender tail began to stretch out, pointing away from the sun. For many astronomers, this was the moment the discovery truly came alive. It was not just a point on a chart anymore, but a comet in motion, showing the familiar signs of activity. That tail was proof that 3I Atlas carried volatile ices, the kind that evaporate when exposed to heat. It was behaving like a classic comet, yet its path revealed it was no local body. This was a comet from another star system, showing its nature in the most visible way possible. Confirming an interstellar object requires more than one telescope. Within days, observatories worldwide joined in. Images flowed in from Chile, Hawaii, Spain, and South Africa. Each one showed the same result: a faint core, a developing coma, and a tail stretching into space. the independent confirmations left little doubt. This was not an illusion or a one-off anomaly. The data were consistent across instruments, across continents. Each new image sharpened the orbit, refining the hyperbolic path that set it apart. The scientific community moved quickly, not with fanfare, but with steady focus. They knew how rare such opportunities were. The confirming images built a consensus that could not be shaken. This was real, and it was extraordinary. Then came one of the most important additions, the Hubble Space Telescope. From its position above Earth's atmosphere, Hubble could capture a cleaner view, free of the distortions of air and weather. Its sharp images revealed details that ground-based telescopes could not. The coma's structure, the alignment of the tail, and the brightness of the nucleus all became clearer. Hubble's confirmation was not just symbolic. It provided data that would be used to guide further study, setting baselines for brightness and composition. With Hubble's eyes added to the effort, the picture of 3I Atlas grew more precise. The interstellar traveler was no longer just a faint speck. It was a fully observed comet, catalogued and confirmed by one of humanity's most trusted instruments in space. The shape that emerged in those first weeks was familiar. A glowing coma surrounded by a faint, elongated tail, exactly the profile that defines a comet. This set 3I Atlas apart from the first interstellar visitor, Oumuamua, which had shown no such features. To see a tail was reassuring in a way. It meant astronomers knew how to study it, using the same techniques that have been applied to comets for centuries. The chemistry, the dust, the outgassing, all could be tracked. It was foreign in origin, but familiar in behavior. That blend of strangeness and recognition made it compelling. This was not just an interstellar rock. It was an active comet, behaving like the ones we know but carrying the history of another star system written into its structure. Comparisons were inevitable. Astronomers thought back to Borisov, the interstellar comet discovered in 2019. Borisov had also grown a bright coma and tail, looking much like the comets of our solar system. In 3I Atlas, they saw echoes of that event. Both showed classic features, both carried volatile ices, and both confirmed that comet-like bodies do indeed travel between stars. Yet 3I Atlas offered something Borisov could not: more warning. Borisov had rushed past quickly, leaving only a short window for observation. Atlas, by contrast, had been spotted early enough to allow for months of careful planning. This meant more telescopes, more instruments, and more opportunities to study its composition in detail. It was, in many ways, the interstellar comet astronomers had been hoping for. Still, memories of Oumuamua lingered. That first interstellar visitor had been baffling, long, thin, and strangely tumbling, without a visible tail. Some had speculated wildly about its nature. Compared to that, 3I Atlas seemed straightforward. It looked like a comet, it behaved like a comet, and its path left no doubt about its interstellar origin. Where Oumuamua had raised more questions than answers, Atlas offered clarity. Yet the contrast only deepened the mystery. Why had the first two interstellar visitors been so different? Was there a wider diversity of interstellar bodies than we imagined? If so, Atlas might represent just one category among many. The contrast between the strange shard of 2017 and the glowing comet of 2025 framed the study of Atlas in a broader context, a growing catalogue of the galaxy's wanderers. By the end of those first observations, there was no longer any doubt. The faint dot had become a well-studied comet, tracked by dozens of telescopes around the globe and above the atmosphere. Its path was confirmed, its interstellar nature secured, and its activity visible for all to see. The sense of certainty was a relief. Astronomers could now move forward with confidence, planning detailed studies of its chemistry and tracking its journey through the solar system. For the wider community, this was the moment of arrival. The discovery was no longer just numbers on a chart. It was real, visible, undeniable. A traveler from another star system had appeared in our skies, and this time we had the tools and the time to truly see it. Calculating the path of 3I Atlas began with a surprise. Its orbit did not close like the paths of normal comets. Instead, the numbers described a hyperbola, an open curve that bends around the Sun and stretches outward again into space. This is the mathematical signature of an interstellar visitor. The calculations confirmed that the object was moving too fast to be captured. Gravity would bend its path but never claim it. Once it passed, it would continue on forever, carrying it back into the galaxy. For astronomers, seeing such an orbit is thrilling. It is proof, written in numbers, that the object does not belong here. A hyperbolic orbit means only one thing. This is a traveler from another system, crossing our skies once before disappearing into the dark. Astronomers often describe a comet's path in terms of its perihelion, the point where it comes closest to the Sun. Every orbit has one, whether it is closed or open. For 3I Atlas, that moment would be its brightest and most active, the time when the Sun's warmth would bring its hidden ices boiling into vapor. Perihelion is not just a point in space, but a moment in time, the peak of a comet's visibility. For an interstellar visitor, it is especially significant because it is the only chance to observe its true character. Afterward, as it recedes, the light fades and the details slip away. Perihelion gives astronomers a deadline. Everything must be ready before that closest approach, because the opportunity will not come again. On October the 30th, 2025, 3I Atlas will reach its perihelion. On that date, it will sweep closest to the Sun, passing within a safe but revealing distance. This will be the moment of greatest activity, when the gases locked inside for billions of years erupt into space, forming the coma and tail in full display. Instruments on Earth and in orbit will be aimed carefully, capturing the spectrum of light, measuring the composition, and following the changes from hour to hour. For astronomers, the date is already circled in their plans. This will be the best opportunity to see the comet as it truly is, before it fades back into the darkness. For a traveler that comes once in history, October 30th will be the peak of its brief performance. Although the comet will pass near the Sun, its course will not bring it particularly close to Earth. At its nearest, it will remain many millions of kilometers away, farther than the Moon by an immense margin, and even beyond the safe distance of ordinary comets that pass near our planet. Yet in astronomical terms, it is still considered a close brush. Close enough that telescopes on Earth can study it in detail. Close enough that amateur observers may glimpse it under dark skies. The approach is distant, but not remote. It is near enough to excite scientists and skywatchers alike, without posing any risk. For most of us, the brush will be invisible. But for the instruments aimed upward, it will be a rare and precious encounter. Mars, too, will have its moment of proximity. As 3I Atlas traces its path around the Sun, it will pass within a respectable distance of the red planet. Not close enough for drama, but close enough to be of interest. Orbiters around Mars may even have the chance to turn their instruments toward it, offering a perspective from another world. The geometry of the solar system occasionally allows such alignments, and when they occur, they add another layer of data. From Earth, from space telescopes, and perhaps even from Mars, this comet will be tracked. Every viewpoint adds a piece to the puzzle, building a fuller picture of the interstellar visitor's journey. Mars may not witness a spectacle, but its instruments could still share in the story. From the start, one of the first questions asked was whether 3I Atlas posed any danger. Objects from beyond can move fast, and a collision would be catastrophic. But calculations quickly ruled that out. The orbit carried it safely past both the Earth and the inner planets. Its closest approach is still far beyond the range of concern. In fact, most comets that originate within our own solar system pass much nearer than this one ever will. The excitement around 3I Atlas is scientific, not defensive. Astronomers can focus entirely on learning from it, without the shadow of risk. That assurance is part of what makes this such a rare gift. We can study a fragment of another system with no fear, only curiosity, knowing it will sweep past quietly and continue on its way. The speed of 3I Atlas is one of its defining traits. Even at its slowest, near the curve of perihelion, it races through space at tens of kilometers per second. That is far faster than the comets bound to the Sun, whose orbits can slow their motion as they climb outward. Atlas is unbound, its momentum carrying it through without pause. For astronomers, this speed is both a challenge and a clue. It makes observation difficult as the comet shifts position each night. But it also confirms its origin. Only an interstellar traveler would move so quickly on a path so steep. Its velocity is a reminder of the vast distances it has crossed, the long journey that began around another star and has now briefly brought it within our sight. Predicting the path of such an object requires precision. Every measurement of its position is fed into models that account for the sun's pull, the pressure of sunlight, and the drag of gases released as it warms. With each new data point, the trajectory sharpens. This is the art of celestial mechanics, turning faint dots on a screen into a map of the future. For interstellar objects, the work is even more delicate, because there is no long history of past orbits to guide the calculations. Everything must be derived from the short window of observations available. Yet within weeks, astronomers had confidence. They could chart its future course, predict its brightness, and know when and where to look. The path was fleeting, but it was no longer unknown. After perihelion, the story will begin to fade. The gases will settle, the tail will grow fainter, and the nucleus will slip back into the cold. Each night, telescopes will track it a little farther from the sun, a little dimmer in the sky. For astronomers, this is both a melancholy and a rewarding phase. The data continues, but the spectacle diminishes. Watching it recede is a reminder of the temporary nature of such events. The object is not ours to keep. It passes through, leaves its record, and moves on. Yet even as it grows faint, its legacy will remain in the images, the spectra, the calculations, and the memories of those who studied it. Watching it fade is part of the rhythm of discovery. In the end, the window is brief. From its first detection to its final disappearance, only months will pass. For an object that has traveled for millions, perhaps billions of years, the time it spends with us is no more than a pause. That is what makes each observation so precious. Every night of data is part of a fleeting opportunity that will not return. When 3I Atlas has gone, it will vanish into the galaxy, likely never to be seen again. The story of its passage will be written in the records we keep, the studies we publish, and the memories of this generation of astronomers. Its visit is a reminder of how vast the universe is, and how rare it is for us to witness even the briefest crossing of its travelers. When a comet approaches the sun, its appearance changes dramatically. At first, it looks like nothing more than a dim speck, a frozen core of rock and ice. But as sunlight strikes it, the outer layers begin to sublimate, solid ice turning straight into gas. That gas escapes into space, carrying dust grains with it. Around the nucleus, a hazy atmosphere forms called the coma. Unlike a planet's atmosphere, the coma is temporary, thin, and constantly replenished by fresh material boiling off the surface. It glows because sunlight scatters off the dust and excites the gas molecules. To astronomers, the coma is a diagnostic tool. Its size and brightness reveal how much material the comet is losing, and its composition shows what kinds of ices lie within. For an interstellar comet, the coma is more than a feature. It is the first real clue to its origin. The trigger for this transformation is simple: sunlight. Even at great distances, the sun's energy can warm the surface of a comet enough to awaken its ices. Water ice, carbon dioxide, carbon monoxide, each has a different threshold. Some vaporize easily, even far from the sun. Others require more heat. In the case of 3I Atlas, the early activity suggested that volatile ices were near the surface. As soon as it neared the inner solar system, jets of gas began to stream out, lifting dust and creating the surrounding glow. This process is both violent and gentle. Violent because gases erupt into space at high speed. Gentle because the comet itself drifts on, intact, with only a thin layer removed. Sunlight is the sculptor, carving patterns of activity on the nucleus and leaving behind a temporary shroud of gas and dust. Dust plays a vital role in the spectacle. As the comet's ices sublimate, grains of rock and carbon are carried outward, suspended in the expanding coma. The solar wind, the constant stream of charged particles from the sun, pushes on this dust, sweeping it into a long, narrow structure. This is the dust tail, the most iconic feature of a comet. Unlike the gases, which glow with specific colors depending on their composition, the dust shines mainly by reflecting sunlight. It is what gives many comets their golden or white trails. For 3I Atlas, the dust tail was an early sign that the object was active, carrying familiar materials despite its alien origin. Each particle of dust is a fragment of another solar system, released into our own, drifting silently on the solar breeze. One of the most curious aspects of comet tails is their direction. People often imagine the tail streaming behind the comet, tracing its path like exhaust. But in reality, tails point away from the sun, not behind the comet's motion. The solar wind is responsible, blowing gas and dust outward regardless of where the comet is heading. This means that as 3I Atlas sweeps around the sun, its tail may at times point ahead of its path, as though it were leading the way. To the eye, this looks strange, but to astronomers, it is expected. The orientation of the tail is a compass needle, always aligned with the flow of energy from the sun. It is a reminder that comets are not passive. They are constantly shaped by the forces around them, their features pointing to the invisible currents of space. As weeks passed, the coma of 3I Atlas grew, and its tail stretched farther into space. Observations showed a veil of gas shimmering in reflected light, a cloud tens of thousands of kilometers wide. Though faint, it was unmistakable. A halo wrapped around a nucleus far too small to resolve directly. The veil gave the comet a presence, a sense of scale that belied its tiny core. For astronomers, it was the first chance to analyze the gases released, to identify molecules through their spectral signatures. For skywatchers, it was a visual confirmation. Here was not just a dot of light, but a living comet, responding to the sun. The shimmering veil was its identity, the cloak it wore as it passed through our skies. For a brief season, it showed itself openly, glowing as sunlight unlocked the ices buried within. Comets are unpredictable. Some remain steady, brightening slowly as they approach the sun. Others erupt suddenly, flaring in brightness as subsurface pockets of gas explode outward. These outbursts can transform a faint comet into a visible spectacle overnight. For 3I Atlas, the question of stability hung in the air. Would it behave like Borisov, steady and reliable, or would it fragment like other fragile comets have done? Early signs suggested it was holding together, its activity gradual, its brightening consistent. Yet no one could say for sure. Comets are fragile, and interstellar comets may be even more so. Each observation was watched closely, not only for the data it carried, but for any sign of sudden change. The balance between stability and outburst was part of the suspense, a reminder that these visitors follow no script. Astronomers soon began comparing the brightness of Atlas' tail with those of familiar comets. It was faint, but not unusually so for a body at its distance. Brightness is a measure not only of how much dust and gas a comet releases, but also of how reflective those particles are. By tracking changes night after night, researchers could estimate the size of the nucleus and the rate of activity. 3I Atlas was modest, neither the brightest comet of the decade nor the faintest. But its significance lay not in its magnitude, but in its origin. Even a small tail from another star system carries more weight than the grandest displays from local comets. The brightness was enough to study, enough to reveal its chemistry, and enough to remind us that light from alien ices was now streaming across our instruments. It wasn't only professional astronomers who watched. Amateur skywatchers joined the effort, training small telescopes on the faint blur. In the best conditions, far from city lights, the comet was within reach of skilled observers. Long exposure photographs revealed its delicate tail, stretching faintly against the star field. Each image shared online added to the sense of participation. People across the world, with modest equipment, were capturing light that had left an interstellar fragment. The involvement of amateurs has always been part of comet science, and with Atlas, it was no different. The data may have been dominated by large observatories, but the joy of seeing it was open to anyone with patience and a clear sky. For many, the glow of Atlas was a personal connection to something truly beyond our world. There is something undeniably poetic about a comet's tail. It is the visible trace of ice turning to vapor, of dust lifted into space, of sunlight and solar wind sculpting matter into a luminous banner. Each tail is temporary, fading as the comet recedes, but for its brief span, it is one of the most beautiful sights in the sky. For 3I Atlas, the tail carries an added weight. It is the trail of a fragment from another star system, a plume of material that once circled a distant sun. To see it glowing now is to witness a history written in light. The poetry is not in metaphor, but in reality, a line of dust and gas, stretched across space, visible to our eyes, carrying with it the story of a world we will never see. By the time Atlas' coma and tail were fully revealed, the discovery had moved beyond doubt. This was not just a statistical oddity, not merely a set of orbital calculations. It was visible, tangible, and behaving as comets do. Its tail was its flag, raised in sunlight, declaring its nature to anyone watching. That flag said two things at once. I am a comet, and I am not from here. In its glow lay the certainty of its identity and the wonder of its origin. The faint smudge that began as a single moving dot had become a comet for the whole world to see. And in that shimmering display was the confirmation that our solar system is not isolated, that visitors do arrive, and that sometimes the universe lets us see them clearly before they pass on. When astronomers study comets, they are not only interested in their orbits, or their brightness. They are especially focused on their chemistry. A comet is a frozen archive, holding ices and dust that preserve the conditions of the place where it formed. By examining what evaporates into its coma, scientists can measure the proportions of gases like water, carbon dioxide, and carbon monoxide. Each tells a story about temperature, distance from the original star, and the mix of elements present. For interstellar comets, this chemical fingerprint is invaluable. It is the closest we can get to holding a sample from another planetary system. Chemistry is what transforms a faint smudge of light into a piece of cosmic history. Every molecule identified adds to our understanding of how worlds form, not just here, but across the galaxy. The James Webb Space Telescope became one of the most important tools in studying 3I Atlas. Webb's infrared instruments are uniquely suited to detecting faint traces of gases in space. While visible light shows us the coma and tail, infrared light reveals what those clouds are made of. Even at great distances, Webb can separate out the signatures of different molecules, identifying them by the way they absorb and emit heat. For Atlas, this capability meant a chance to peer directly into its chemistry, to measure what kinds of ices were escaping as it warmed. No other instrument could provide such detail from so far away. With Webb, astronomers were able to look beyond the comet's glow and into the building blocks locked within, offering the first real glimpse of its alien composition. The first spectra of 3I Atlas brought both excitement and surprise. As the light from its coma was split into its component wavelengths, clear lines appeared, marking the presence of familiar molecules. Water vapor, as expected, was there. But other lines stood out more strongly than anticipated. Carbon dioxide, in particular, was abundant, more than seen in many comets of our own system. The surprise was not just in the presence of these gases, but in their relative strengths. The ratios did not match the averages from comets born around the Sun. For scientists, this was the most valuable outcome. It meant that 3I Atlas was truly carrying the chemical story of another system. Its differences were not noise, but signal, pointing to conditions unlike those in our own cosmic neighborhood. Carbon dioxide quickly became one of the defining features of 3I Atlas. As the comet warmed, it released CO2 in large amounts, filling the coma and powering much of its activity. On Earth, carbon dioxide is common, part of our atmosphere and climate. In comets, its abundance can vary widely. For Atlas, the levels were striking. This suggested that in its home system, the comet formed in a region rich in carbon-bearing ices. It also meant that its activity could be driven strongly even at large distances from the Sun, since CO2 sublimates more easily than water ice. This abundance gave astronomers a direct clue about the environment of its birth, a place cold enough to freeze carbon dioxide, yet rich enough to trap large amounts of it in its core. One of the key numbers astronomers studied was the ratio of carbon dioxide to water in the comet's emissions. In comets of our solar system, this ratio tends to fall within a certain range, reflecting the conditions of the early solar nebula. For Atlas, the ratio was different, noticeably higher. This was not a small fluctuation, but a clear signal. It suggested that comets formed around other stars can have distinct chemistries, shaped by their own unique disks of gas and dust. Such differences are the entire reason interstellar comets matter. They show us that the recipe for planets and small bodies is not universal. Variations exist, and by measuring them, we expand our picture of how diverse planetary systems can be. The CO2 to H2O ratio of Atlas is one of its most telling fingerprints. Carbon monoxide, though less abundant, carried its own significance. SeO sublimates at very low temperatures, so its presence reveals conditions in the coldest parts of a planetary system. Detecting CO in Atlas meant that some of its ices had been preserved from an extremely frigid environment. This detail helped place constraints on its likely birthplace. It must have formed far from its star, in a region where even the most volatile ices could freeze solid. For astronomers, the detection of CO was like finding a time capsule from the edge of another planetary disk. It was proof that Atlas was not only interstellar in path, but in chemistry, carrying with it the signature of a world that may have resembled the far outer reaches of our own solar system. Once the chemistry of Atlas was clear, comparisons with our own comets began. Borisov, the interstellar comet of 2019, had shown some similarities to local comets, though with subtle differences. Atlas, by contrast, showed more striking shifts in its chemical ratios. Against the backdrop of solar system comets, it stood apart. This was exactly what astronomers hoped for, a clear example of diversity among planetary systems. If Borisov had suggested some similarities, Atlas highlighted differences. Together, they showed that interstellar comets are not uniform. Each is shaped by its own star and its own disk of material. By comparing them, we gain a richer understanding of how planets and comets form, not as a single story, but as many, scattered across the galaxy. The chemistry was not limited to gases. Dust grains released from Atlas also told their story. Analyzing how light scattered through the coma, astronomers could infer the size and composition of the dust. Some grains were tiny, comparable to smoke particles. Others were larger, more like fine sand. The mix affected the color of the comet's glow, giving clues to the minerals locked within. Dust analysis is subtle, requiring both spectroscopy and careful modeling. Yet even this faint data is revealing. Each dust grain was once part of a solid world orbiting another star. Now, carried into our solar system, those grains became messengers. Their properties spoke of conditions billions of years and light years away. Dust is less dramatic than gas, but it is just as telling. Together, gas and dust create the full portrait of an alien comet. One of the most remarkable aspects of Atlas was how quickly its chemistry was confirmed worldwide. Observatories across the globe, from Chile to Hawaii to Europe, pointed their instruments at it. Data poured in, often shared almost in real time. Each team confirmed the signatures of CO2, H2O, and CO. Each added refinements, reducing the uncertainty, sharpening the ratios. The global collaboration ensured that no single telescope carried the burden. It also showed the strength of modern astronomy. An event of this rarity could be studied in detail by a coordinated network spanning continents. This shared effort gave confidence that the chemistry was real, not a fluke of any one instrument. The chemical fingerprint of 3I Atlas became one of the most thoroughly cross-checked results of the year. By the close of its chemical study, Atlas had gone from a faint speck of light to a fully profiled interstellar visitor. Its gases were identified, its dust measured, its ratios compared. Each line in its spectrum became a sentence in its story, telling us where it had formed and what it carried across the galaxy. Chemistry had revealed not just the comet's structure, but its history. It was the closest humanity had ever come to sampling another planetary system directly. Though the comet itself would pass on, the data remained, a library of molecules, frozen long ago, awakened in our skies, and written into our instruments. In its chemistry lay the revelation we sought, proof that the galaxy holds many recipes for creating worlds, and that sometimes those recipes pass briefly within our reach. The Milky Way is not a uniform place. It is a vast spiral galaxy with distinct neighborhoods, each with its own history. Closest to us is the thin disk, where most of the bright stars and gas clouds lie. This is the bustling, active region where new stars continue to form. Surrounding it is the thick disk, older and less crowded, filled with ancient stars that date back to the early days of the galaxy. Beyond that lies the halo, sparsely populated with clusters and streams of stars left over from long-ago mergers. Where 3I Atlas came from is not known, but its orbit through the solar system hints at its larger context. Its velocity and trajectory suggest it is not part of the thin disk where the Sun resides, but from an older, quieter neighborhood of the Milky Way. That fact alone gives it weight. Astronomers describe the thick disk as a kind of fossil record of the galaxy. It is home to stars that are older, poorer in heavy elements, and spread across a wider vertical band above and below the plane of the Milky Way. Unlike the thin disk, it does not teem with star formation. Instead, it is a region of stability, where ancient stars drift with slower, puffed-up motions. If 3I Atlas truly comes from the thick disk, then it carries the imprint of that ancient population. Its chemistry, its ices, and even its dust could reflect conditions that were present billions of years ago, before the Sun itself had formed. The thick disk is not the brightest part of the galaxy, but it is one of the oldest. Objects from this region are messengers from a time long before our own neighborhood came into being. The idea that 3I Atlas may be older than the Sun is staggering. Our star is about 4.6 billion years old, already ancient by human standards. But the thick disk contains stars and systems that may be twice that age, or more. If Atlas was born there, then its ices condensed in a protoplanetary disk long before Earth even existed. This is not just an interstellar traveler. It may be a relic from an earlier chapter of the galaxy's history. Studying it is like holding a fragment of deep time, a record not just from far away, but from long ago. Few objects can give us such a direct connection to the past. Each molecule in its coma is a piece of evidence, unchanged since an age when our Sun had not yet been lit. To speak of billions of years can make the numbers feel abstract, but their meaning is clear. Over such timescales, stars are born, live their lives, and die. Entire planetary systems form and vanish. Galaxies collide, and new structures emerge. For Atlas to still exist after billions of years means it has survived cosmic upheavals intact. It has not been melted by a star, nor shattered in collisions, nor consumed by larger bodies. It has simply drifted, cold and unchanged, across the galaxy. That survival is part of what makes it so valuable. It is not only a relic of another system, it is a survivor of time itself. Billions of years are written into its presence, an unbroken chain of history preserved in a body small enough to pass unnoticed until now. How did it arrive in interstellar space? The answer is ejection. In the early days of planetary systems, giant planets often scatter smaller bodies. Their gravity slingshots comets outward, sometimes into new orbits, sometimes beyond the reach of their star entirely. Billions of such objects may be cast adrift by each system. Atlas was almost certainly one of them. Born in the outer reaches of a young star's disk, it was nudged and pulled until a massive planet hurled it into interstellar night. That moment ended its connection to its home star forever. From then on, it became a wanderer, no longer bound, carrying with it only the chemistry and structure it had acquired in its birthplace. Its journey as an interstellar traveler began with that violent, decisive push. Once free, Atlas entered the slow crossing of interstellar night. For billions of years, it drifted through the spaces between stars. In that void, there is little to change it. Cold kept its ices frozen solid. Distance kept it beyond the influence of any one star. It moved with steady momentum, unhurried, unaffected, simply crossing the galaxy in silence. The emptiness preserved it. While planets changed, stars evolved, and galaxies collided, Atlas endured without alteration. It may have passed through diffuse clouds of gas or through regions shaped by ancient supernova, but none of it altered its path. Its slow voyage is part of what gives it value. It is not just a fragment of another system, it is a fragment that has carried its message faithfully for ages beyond comprehension. Yet even in interstellar space, encounters can occur. Stars move, clusters drift apart, and sometimes two systems pass near enough to disturb their comets. Over billions of years, Atlas may have felt the tug of passing stars, each one altering its course slightly. These encounters are difficult to trace. The galaxy is dynamic, with every star in motion. By now, whatever star once gave birth to Atlas is lost among millions of possibilities. The comet's path is a record of countless interactions, most too subtle to identify. But they are part of its journey. Stellar flybys may have shifted it closer to our region of the galaxy, eventually guiding it into the neighborhood of the Sun. The randomness of those encounters is why we see it now, and not countless other fragments that remain hidden. For all our calculations, we may never know which star Atlas truly came from. Its path has been bent too many times, its history too long. Over billions of years, even small uncertainties compound into impossibility. We can model its general origin, but not pinpoint a single home. To many astronomers, that is part of its beauty. It remains a messenger without an address, carrying only its chemistry as evidence. Its anonymity makes it universal. Atlas is not tied to a single story, but to the larger story of the galaxy. It could have come from any one of 1,000 suns, and that uncertainty reminds us how connected all systems are. Its home is the Milky Way itself, not any one star within it. Even without a definite home star, statistics can offer hints. The velocity of Atlas, the tilt of its orbit, and its direction of entry all suggest membership in the thick disk. This is not proof, but probability. Its chemical differences from solar system comets align with this idea, suggesting it formed in an older, colder environment. By comparing many such interstellar objects, astronomers hope to refine these guesses. Each one adds to a growing sample, a survey of comets from across the galaxy. With time, patterns will emerge. Already, Atlas strengthens the case that interstellar comets come from diverse origins, reflecting the many environments where stars and planets take shape. It is statistical reasoning, not certainty, but it is enough to broaden our view of the galaxy's richness. As Act V draws to a close, we can see 3I Atlas, not just as a comet, but as a traveler carrying the memory of its birthplace. It was formed in another star's nursery, scattered into the galaxy, and preserved for billions of years. Along the way, it crossed through regions we cannot map, past stars we cannot name, until at last it brushed near our Sun. Its migration is cosmic in scale, a journey from one neighborhood of the galaxy to another, across time as well as space. We may not know its exact origin, but we know enough to marvel. It is a fragment of the system long gone, carried faithfully until now. Its path reminds us that migration is not only for living beings, it is the nature of matter itself, drifting endlessly through the Milky Way. The discovery of 3I Atlas set off a quiet but determined race. Once the faint point was flagged, every hour mattered. Interstellar visitors move quickly, and they do not wait for our convenience. Observatories scrambled to adjust their schedules, slipping in brief observations between other projects. The first goal was simple: confirm the object's unusual orbit. After that, the task grew larger. Capture as much detail as possible before the comet grew faint again. Teams across continents coordinated in near real time, sending updates, sharing preliminary plots, and refining predictions. It was not a competition in the usual sense. It was a collective rush, an understanding that everyone was working against the same ticking clock. The race was not to claim the discovery, but to preserve the opportunity. The comet had offered its presence. Humanity now had to listen, quickly but carefully, before it was gone. Coordinating telescopes around the world is a delicate dance. No single observatory can watch the sky at all times. Clouds roll in, the Earth rotates, and night falls at different hours. To keep track of a fast-moving comet like 3I Atlas, astronomers relied on a global network. As the object set in one location, it rose in another. Observers in Chile could hand off to colleagues in Spain, who then passed it to those in Hawaii. The data flowed in a continuous chain, like a relay race across the planet. Software helped combine the measurements, updating the orbit with each new set of coordinates. What might have been a fleeting glimpse became a steady watch, made possible by cooperation. The comet itself knew nothing of this worldwide effort, but it inspired a level of coordination that few natural events can summon. Among all the instruments brought to bear, the Hubble Space Telescope carried a special weight. Suspended above Earth's atmosphere, it could see the comet without the blur of air. Hubble had already played a role in confirming 3I Atlas' presence, but its continued observations promised more. Its sharp vision could resolve the structure of the coma, tracing jets and measuring brightness with unmatched precision. Hubble had also studied the earlier interstellar visitors, providing a thread of continuity across all three discoveries. In the case of Atlas, it added depth and clarity, showing faint details that ground-based telescopes might miss. For astronomers, Hubble's involvement was both practical and symbolic. It tied the study of Atlas to a long legacy of discoveries, showing how instruments above Earth can extend our reach into the cosmos. On the ground, anticipation was building for another instrument, the Vera C. Rubin Observatory in Chile. Still preparing for its first full surveys, Rubin was designed to scan the entire visible sky every few nights, capturing deep images with a massive camera. Its mission is to track changes, to watch the universe in motion. For interstellar visitors, Rubin promises earlier detection, giving scientists more time to prepare. With Atlas, astronomers had only a few months to observe before the comet faded. With Rubin, future visitors might be found years in advance, offering the chance to plan spacecraft missions. Though Rubin was not yet fully online during Atlas' passage, its potential was clear. This discovery served as a preview of what might come. In the future, when another interstellar traveler approaches, Rubin could be the first to see it. The case of 3I Atlas showed why early detection matters. Comets brighten as they approach the sun, but they also move faster, racing past before telescopes can capture much detail. With only days or weeks of warning, as happened with Oumuamua, opportunities are lost. With months of preparation, scientists can schedule the most powerful instruments, coordinate across observatories, and focus on the moments of greatest activity. Early detection also raises possibilities beyond observation. With enough time, future missions might launch probes to meet such visitors directly. The sooner we know, the more we can do. Atlas was discovered earlier than its predecessors, but it was still only months away. The lesson was clear. The earlier we spot these travelers, the more fully we can learn from them before they vanish into the dark again. Behind the scenes, a quiet hub kept the entire effort moving smoothly. The Minor Planet Center, hosted by the Smithsonian Astrophysical Observatory, is the global clearinghouse for small body observations. When Atlas first detected the moving dot, the data flowed quickly to the center. There it was posted for astronomers worldwide to examine. As new measurements came in from other observatories, the center combined them, refining the orbit and distributing updates. This system has existed for decades, tracking asteroids and comets, but it has become essential for interstellar discoveries. Without it, no single group could keep pace. The Minor Planet Center served as the central nervous system of the search, ensuring that every observer, from major telescopes to small amateur setups, was working with the same information. In the study of Atlas, this coordination was as important as the observations themselves. In earlier eras, data from a discovery might take months to circulate. Today, information moves almost instantly. Observers who detected 3I Atlas shared their results online within hours. Spectra, orbital solutions, and brightness estimates were posted to public databases where anyone could see them. This openness allowed dozens of teams to act at once, each adding to the collective effort. The flow of data was constant, almost like a conversation held across continents. For scientists, it was a reminder of how far collaboration has come. For the wider public, it offered a chance to follow along in real time, watching a discovery unfold. In the case of Atlas, transparency was as important as technology. The comet became not just an object of study, but a shared experience, a story written together by people scattered across the Earth. The discovery also opened doors for students. Universities and observatories often involve young researchers in follow-up observations, data analysis, and modeling. For many, 3I Atlas became their first chance to work with data from a truly interstellar object. Some spent long nights operating telescopes, adjusting instruments, and sending their measurements to the global network. Others worked with the spectra, learning how to identify faint molecular signatures. These experiences were more than academic exercises. They were direct participation in a once-in-a-lifetime event. For students just beginning their careers, Atlas was a reminder of why they had chosen astronomy in the first place. The chance to contribute to a discovery of this scale was both humbling and inspiring, a moment that might shape their work for decades to come. Amateur astronomers also played a role. With modern digital cameras and modest telescopes, skilled observers around the world were able to track 3I Atlas as it brightened. Their long exposure images revealed its faint tail, sometimes before professional telescopes could confirm changes. These photographs, shared across online forums and communities, created a sense of connection. People from different countries compared notes, checked each other's work, and added to the pool of knowledge. The comet became a shared project, not only among scientists, but among enthusiasts who watched the skies for pleasure. This partnership between professionals and amateurs has deep roots in astronomy. With Atlas, it reached across the globe, uniting thousands of eyes on a single distant traveler. By the time the data began to converge, the picture was clear. A faint dot had become a comet, and its story was being told by many voices. Telescopes on mountaintops, space observatories above the atmosphere, and backyard astronomers with patient eyes all contributed. The result was not a single viewpoint, but a symphony of perspectives, each adding depth and detail. Science at its best is rarely a solitary act. It is a collective effort built from cooperation, patience, and trust. The study of 3I Atlas embodied that spirit. In its brief passage through our skies, the comet brought together a community across the world. It reminded us that discovery is not only about what we learn, but about how we learn, together, listening carefully and sharing what we find. There comes a point when numbers, though essential, can feel incomplete. The orbit of 3I Atlas can be described with equations, its chemistry with ratios, its brightness with magnitudes. Yet those details, while precise, do not capture the full experience of such a visitor. To appreciate it fully, we must set the equations aside for a moment and look with different eyes. Beyond data and models, there is the simple reality of what it means to see a comet from another star. It is a point of light with a story, a fragment of a distant world entering our sky. The facts are important, but they are not the whole picture. For many who watch, what matters is not only what we learn, but how it feels to witness something so rare. Science gives us the framework. Curiosity and wonder fill in the rest. To imagine Atlas clearly, think of it not as a number on a chart, but as an object glowing faintly in the night. Through a telescope, it is a soft blur, surrounded by a hazy coma. A delicate tail stretches outward, faint but persistent, always pointing away from the sun. Its light is subtle, requiring patience to detect, but once found, it has a quiet presence. Unlike stars, which shine with steady points, the comet looks diffuse, as though it carries its own atmosphere. It drifts slowly from night to night, its position changing against the star field. For astronomers, this sensory portrait is what balances the data. The comet is not abstract. It is visible, tangible, even if faint. Atlas is both a subject of measurement and an object of beauty, a presence that invites careful, lingering attention. The colors of Atlas tell their own story. To the eye, through most small telescopes, it looks pale, whitish or slightly green, depending on the filters used. That green tint comes from molecules of carbon-based gases, glowing when struck by sunlight. Cameras can capture the subtle hues more clearly, showing faint blues in the tail and a soft yellow in the dust. These colors are not just visual decoration. They are the fingerprints of chemistry, each one tied to a specific molecule or grain. Yet they also matter in a different way. They remind us that this comet is real, shining with its own light, not an abstract point. When people share photographs of its faint glow, they are sharing a color palette carried across interstellar space. The shades of Atlas are the shades of another system's chemistry painted briefly across our sky. It is natural to wonder what the nucleus of Atlas looks like up close. We cannot see it directly, its coma hides the solid core. But by comparing it to comets we have visited with spacecraft, astronomers can imagine it. Likely it is irregular, dark, and pitted with craters and cliffs. Its surface would be coated with ancient dust, broken by vents where gas escapes. Some regions may be smooth from past outgassing, while others are jagged. The nucleus may only be a kilometer or two across, a tiny world by any measure, yet it carries within it the record of its star's nursery. Imagining its surface is not idle fantasy. It is a way of connecting the faint blur we see from Earth with the real, physical body that lies at its heart, an alien worldlet, drifting silently through space. The silence of 3I Atlas is one of its defining qualities. It makes no sound, no vibration, no signal we can hear. It moves through the solar system without stirring the vacuum around it. Yet this silence is not empty. It is the silence of age, of distance, of countless years spent in the spaces between stars. For astronomers who observe it, the quiet is part of the experience. Looking at Atlas is to look at something utterly indifferent, something that has no awareness of our attention. Its silence is both humbling and calming. It reminds us that the universe is vast, that not everything is made for us, and yet we have the tools to notice and appreciate it. In that way, the silence of the comet is not absence, but presence, an invitation to reflect in stillness. Long before comets were understood scientifically, they carried a heavy weight in human culture. Across civilizations, a comet's sudden appearance was seen as a sign. Some regarded them as omens of disaster, warnings of famine, war, or the fall of kings. Others saw them as heralds, marking great changes or divine messages. Their unpredictable arrivals gave them power. Unlike the steady stars, comets came and went without warning, breaking the order of the heavens. Even in art and literature, they were drawn as blazing swords or torches in the sky. This history reminds us that comets are not only scientific objects. They are also cultural ones, woven into our stories and fears. Atlas, though interstellar and rare, fits into this same tradition. It too is a sudden visitor, unannounced, stirring wonder and meaning as it passes. Specific stories of comets as omens are found across time. In China, ancient astronomers carefully recorded their appearances, linking them with dynastic changes. In Europe, Halley's Comet was painted above the Battle of Hastings, imagined as a sign of the Norman conquest. Even as recently as the 19th century, comets inspired fear when their tails were thought to carry poisonous gases. These stories were not superstition alone. They were attempts to understand events that seemed beyond human control. A comet appearing in the sky was too striking to ignore. It had to mean something. Today, we no longer fear their presence, but the stories linger. They are part of the cultural fabric that shapes how we respond. When Atlas was announced, the language of omens did not return, but the old sense of awe did. The human response has always been layered. The line between science and myth is not always sharp. Both begin with noticing the unexpected and trying to explain it. Where myth used stories of gods and fate, science uses data and models. Yet both respond to the same impulse to make sense of the sky. With comets, the overlap is clear. The same glowing tails that once inspired fear now provide spectra for chemistry. The same sudden arrivals that seem to announce doom now trigger coordinated research campaigns. Science does not erase the mythic past. It builds on it, transforming fear into knowledge. With Atlas, this transformation is on display. It is a comet we can measure, yet also one we can admire. A visitor that inspires both rational curiosity and emotional wonder. Science and myth are two languages telling the same story. The sky is alive with meaning. Imagination plays a quiet but powerful role in discoveries like Atlas. Data tells us the orbit, the chemistry, the brightness. But imagination lets us see further, what its surface might look like, where it might have formed, how many others like it may be drifting unseen. Imagination also bridges the gap between science and personal experience. It allows someone looking through a small telescope to feel connected to another star system. It allows scientists to consider futures where spacecraft intercept such visitors, bringing back samples. Without imagination, the data would remain confined to charts. With it, the comet becomes a story, an event, a presence in human thought. Atlas does not just inform us, it stirs the mind, inviting us to picture what lies beyond our reach. That act of picturing is as important as the measurements themselves. As Act the 8th closes, we leave the equations behind and sit with the larger meaning. Atlas is a comet, yes, but it is also a symbol. Its faint glow in our sky is both a physical event and a reminder of the universe's depth. It has no voice, but it speaks through its silence. It has no message, but it carries the imprint of another star. In its passing, it draws together science and culture, fact and imagination, precision and poetry. To listen to Atlas is not to hear sound, but to feel perspective. It reminds us that discovery is not only about data, but about wonder. When we pause to watch such a traveler, we are reminded of our place in the galaxy. Sometimes the greatest lesson lies not in answers, but in the quiet act of paying attention. Patience is one of the first lessons Atlas offers. The comet was faint, subtle, and easily lost against the crowded star fields of the Milky Way. Detecting it required time to take repeated images, to compare them carefully, to notice the slight shift from one frame to the next. In an age of instant answers and rapid results, the discovery of an interstellar comet is a reminder that some things cannot be rushed. The universe moves on its own schedule. Our role is to wait, to watch, and to be ready when the rarest events unfold. Atlas did not reveal itself in a single dramatic flash. It emerged gradually, its story built from patience. For astronomers, that patience is more than a practice. It is a way of seeing. And for the rest of us, it is a gentle reminder that wonder often rewards those willing to wait. Careful observation is at the heart of astronomy, and Atlas highlighted this discipline. The comet was not discovered by accident, nor by chance glances at the sky. It was found through systematic surveys, precise instruments, and meticulous attention to detail. Once noticed, its path had to be tracked night after night, with tiny measurements confirming its motion. This work is quiet and methodical, far removed from the excitement of headlines. Yet it is exactly this discipline that turns faint pixels into certainty. Without rigor, the discovery would have faded into doubt. With it, Atlas became a milestone. The lesson here is simple. Science advances not only through bold theories, but through careful, repeated effort. The discipline of observation is what allows us to distinguish noise from truth, to find significance in the faintest flickers of light. Science is often about predicting what should happen, but it must also be prepared for surprise. Atlas was such a surprise. No one knew when the next interstellar object would appear, nor what it would look like. Yet when it arrived, astronomers were ready to adapt. Observing schedules were changed, instruments repurposed, and research plans rewritten. This flexibility is part of the scientific method. Discovery does not always follow the script. Surprises test our ability to respond, to gather data before the opportunity is lost. Atlas reminded the community that readiness is not just about technology, but about mindset. Expect the unexpected and be willing to follow where the evidence leads. In handling surprises gracefully, science shows its resilience. It is not disturbed by the unexpected. It is energized by it, turning surprise into knowledge. Not every surprise should be treated as sensational, though, and Atlas provided an example of restraint. When Oumuamua was discovered in 2017, its strange shape and lack of a coma fueled wild speculation, including ideas of alien spacecraft. The debate overshadowed the careful science being done. With Atlas, the response was calmer. The data spoke clearly. This was a comet, active, with a tail, behaving in familiar ways. Astronomers resisted the urge to exaggerate. The significance was real enough without embellishment. By keeping the focus on evidence, they avoided the pitfalls of hype. This balance is important. Sensational claims may capture attention, but they can erode trust. Atlas demonstrated that wonder does not require exaggeration. A comet from another star system is extraordinary on its own. The truth was more than enough to inspire awe. The wonder of Atlas lies precisely in its unexpected nature. It was not predicted, not scheduled, not guaranteed. It appeared suddenly, as comets always do, but with the added weight of being interstellar. That combination gave it a sense of rarity that few astronomical events can match. The unexpected has power. It interrupts routine, it breaks the steady rhythm of the sky, and it invites us to look up with fresh eyes. Atlas was not a spectacle in the way a bright eclipse or meteor shower might be. It was quiet, subtle, and easy to miss. Yet that very quality made it special. The unexpected does not always shout. Sometimes it whispers, and the wonder is in noticing. Atlas reminds us that the universe still has the capacity to surprise, even when we think we know its patterns. Turning faint pixels into poetry is one of the hidden arts of astronomy. At its heart, the discovery of Atlas was a collection of images, data points, and spectral lines. To a casual observer, these are abstract and technical. Yet from them emerges a story, a comet born around another star, ejected into the galaxy, drifting for billions of years and passing briefly by our sun. That transformation, from data to narrative, is part of what makes astronomy resonate with people. Scientists analyze numbers, but they also translate them into meaning, into stories we can hold on to. Atlas became more than a charted orbit. It became a messenger, a traveler, a fleeting guest. The poetry does not replace the science, it flows from it. Numbers tell us what it is. Imagination tells us why it matters. Together, they create the full picture. It is natural to imagine the beginning of Atlas' journey. Long ago, in a distant star system, a protoplanetary disk circled a young star. Within it, dust grains stuck together, forming icy clumps. Over time, one of these clumps became the comet we now call Atlas. Perhaps it orbited peacefully for millions of years, until a giant planet's gravity altered its path. In one decisive encounter, it was flung outward, its bond to its star broken forever. That moment set it on a course into interstellar space. The star that birthed it may still shine somewhere in the galaxy, but its comet is gone, wandering. Imagining that start adds dimension to what we see now. Atlas is not just a faint light in our sky. It is the survivor of a story billions of years old, beginning in a place we can never visit. The lessons of Atlas are enriched by remembering past visitors. Oumuamua, strange and silent, showed us that interstellar bodies can take forms we do not expect. Borisov, with its bright tail, demonstrated that some behave much like local comets. Atlas now adds a third chapter, confirming both variety and familiarity. Together, these discoveries sketch the outlines of a broader picture. They remind us that each visitor is unique, yet each belongs to a larger population we are only beginning to glimpse. Past visitors taught us humility and caution, patience and imagination. Atlas continues that tradition while adding its own distinct voice. In learning from all three, we see the importance of persistence. No single object tells the full story. Only by gathering lessons from many can we hope to understand the galaxy's drifting fragments. Astronomers speak of building a cosmic census, and interstellar objects are part of that effort. Just as we count stars, galaxies, and exoplanets, we now aim to count the travelers that pass between systems. Atlas contributes to that census, one more data point in a growing catalogue. With time, the numbers will reveal patterns, how often such objects appear, what they are made of, and what they tell us about their origins. Each one is like a survey form filled out by the galaxy itself, offering clues about the diversity of planetary systems. The census is still small, but it is growing. Atlas is not only an isolated event. It is a piece of a larger puzzle, helping us measure the unseen traffic of matter through the Milky Way. In that way, it transforms from a curiosity into part of a larger framework of knowledge. As Act the Ninth closes, we step back and place Atlas in perspective. It is rare, but not unique. It is faint, but full of meaning. It is fleeting, but its lessons endure. For scientists, it is data, spectra, and models. For the wider world, it is a reminder of our place in the galaxy. It tells us that our solar system is not isolated, that fragments of other stars can and do enter our skies. It shows us that discovery is not always about spectacle, but about attention. Atlas does not ask to be noticed, but it rewards those who do. In its perspective, we see both the vastness of the universe and the power of careful observation. It is, in the end, a story of connection between stars, between systems, and between the human search for knowledge and the quiet wonders of the sky. The story of 3I Atlas is above all a fleeting one. For a few short months, it drifts through our skies, offering us the chance to notice and learn. Then, just as quietly as it arrived, it will vanish into the dark. This briefness is part of its beauty. It is like a friendship made in passing, a traveler encountered on the road who shares a story before moving on. The encounter is temporary, but it leaves an impression. Atlas is not here to stay, but in the time it is with us, it deepens our sense of the universe. Its fleeting presence is a reminder that not all connections are lasting. Some are valuable precisely because they are brief, moments of contact that shine against the backdrop of eternity. Atlas is a comet of impermanence, and in that impermanence lies its meaning. Thinking of Atlas reminds us that the universe is more neighborly than it sometimes seems. Stars may be separated by light years, but fragments of their systems can wander, cross paths, and enter each other's skies. Our solar system is not sealed off, nor are others. Material is exchanged across the galaxy, not in torrents, but in rare, meaningful encounters. When a comet like Atlas enters our view, it carries with it the suggestion that we are part of a larger web. Other stars have touched our skies indirectly, sending their debris to brush against our world. This sense of neighborhood is vast and quiet, but it is real. Atlas is not an isolated body. It is proof that the galaxy is interconnected, that stars share more than light, and that across the immensity of space, there are still threads of contact. What happens after Atlas leaves? The answer is simple. It keeps going. Its hyperbolic orbit carries it out of the solar system, back into interstellar space. It will pass into the cold, dark regions between stars, where it will drift indefinitely. Perhaps it will wander for billions more years, untouched. Perhaps one day, far in the future, it will pass close to another star, where another civilization might see it and wonder at its origin. For us, though, the story ends here. Once it grows faint, it will be beyond the reach of our telescopes. The comet itself will continue, but its chapter in our history will be finished. The beauty of its visit lies not in permanence, but in its passage, a brief arc of light before returning to the silence from which it came. Though Atlas itself will move on, the data it leaves behind will remain. Every image, spectrum, and orbital calculation adds to a permanent archive. Researchers will study these results for years, comparing them with future discoverers, refining theories, and searching for patterns. The comet may fade from sight, but its fingerprints will live on in our records. In a sense, the data is a shadow of the comet, a trace left behind that others can revisit. Even long after the object is gone, scientists will continue to learn from it. The raw numbers will be reanalyzed, the chemistry reconsidered, the trajectory compared with those of new visitors. Atlas will join the growing database of interstellar objects, its presence carried forward not in light, but in knowledge. The discovery of Atlas also plants seeds for the future. Each interstellar visitor strengthens the case for preparing missions to intercept them. Imagine a spacecraft on standby, ready to launch when the next object appears. With enough warning, we could send instruments to fly alongside, sampling the gases directly or even returning material to Earth. Atlas could not be reached this way. Its discovery came too late, but it fuels the dream of such missions. The comet is a reminder that these opportunities are real, not hypothetical. The next visitor might be found early enough, with technology advanced enough to make contact. Atlas may pass quietly, but its legacy could be to inspire the tools that one day let us hold a fragment of another star system in our hands. If 3 interstellar objects have been found in less than a decade, it suggests there are more to come. Atlas is not unique in existing, only in being noticed. The galaxy is likely filled with such wanderers, countless fragments drifting unseen. With improved surveys, we may detect them more often, each one adding a piece to the puzzle. Atlas shows the promise of this future. Its chemistry, its orbit, its behavior, all of these contribute to a growing catalogue. As the list expands, we will see patterns emerge, and perhaps even identify the kinds of stars most likely to send us visitors. The promise of more interstellar comets is not speculation, it is expectation. Atlas is a beginning, not an end, a hint of the many travelers still waiting to be discovered. Every discovery like Atlas changes our maps, not just of space, but of thought. Before 2017, no interstellar object had ever been confirmed. Now, with 3 known examples, we must redraw our understanding of the solar system's place in the galaxy. Our maps now include not just the planets, asteroids, and comets bound to the Sun, but the occasional visitors from beyond. These visitors remind us that the solar system is open, porous, connected. They extend the borders of what we consider local, showing that the galaxy is not a distant backdrop but a place of exchange. Atlas expands the frontier of our knowledge, marking the solar system not as a closed system, but as a waypoint in the broader currents of galactic matter. Our maps will never again be complete without including the paths of such wanderers. The human response to Atlas is as important as the data. For astronomers, it is a chance to study, to publish, to refine theories. For the public, it is a chance to feel awe, to look up and imagine. News of Atlas spread not with alarm, but with quiet wonder. People shared images, asked questions, and followed the story. In a world often consumed with immediate concerns, the appearance of an interstellar comet created a moment of perspective. It reminded us that there is more beyond our daily lives, that the universe is vast and filled with surprises. The human response, in all its forms, is what gives meaning to discovery. Without it, the comet would still pass, but unnoticed. With it, Atlas becomes part of our shared history, a story remembered long after the light itself has faded. Eventually, the time will come for a quiet farewell. Atlas will slip beyond visibility, fading into the distance. Telescopes will record it one last time, and then it will be gone. No fireworks, no spectacle, just the end of a passage. Saying goodbye to such an object carries a mix of emotions. There is gratitude for what it revealed, and sadness that it will not return. But there is also acceptance. Comets are wanderers, and interstellar ones more so. They are not ours to keep. They pass through, they remind us of the galaxy's breadth, and then they continue on. The farewell is part of the experience, a reminder that beauty often comes in fleeting form. Atlas will leave us, but in doing so, it will have left us richer in knowledge and deeper in perspective. Tonight, we followed the journey of an interstellar traveler, a comet from another star, and one of the rarest discoveries of our time. We've seen how it was found, how it revealed its chemistry, how it connected us to distant parts of the Milky Way, and how it reminded us of the quiet wonder hidden in the night sky. These stories are here not just to inform, but to ease you into rest, with curiosity as a gentle companion. If you've enjoyed this exploration, I invite you to like, subscribe, or share your thoughts in the comments. It helps us reach more curious minds, and it means these journeys can continue. But for now, let the thought of distant comets drift softly in your imagination. The universe is wide, the night is calm, and sleep is waiting. Until next time, rest well.